Okay, so welcome back. And so now what we're going to talk about are things called cycloids, and we're going to talk about other types of parametric curves as well, like hypercycloids, hypocycloids. But let's talk about the cycloid to start with. Okay, so what is a cycloid? Okay. First, let's picture what's going on here. Okay, so a lot of things, we have different curves that happen in real life, in physics and mechanics and things like that. So one of the things is let's visualize a circle, right? Whether it's a wheel, right? And let's say a bicycle wheel, that's a common example, but let's say we have a circle, and let's say this represents, let's say, a bicycle, and we've got the center of the bicycle, and it's rolling on a flat surface, and it's not slipping, okay? So it's just rolling along, and what we're going to do is we're going to mark one of the tire. We're going to mark the tire like with chalk, okay, with the yellow line, okay, and we're going to follow the path that mark travels as the wheel rolls on the flat surface. So, how do we graph this path? Okay, well, you can see by the blue line that the path this is going to take is going to have something like this. Okay, and if it rolls the other way, the dot, again, we're talking about this mark here on the edge of the circle. It's going to follow this path, okay, and it's also going to follow this path if you rolled it the other way. Okay, so we want to describe this path, right? This is this parametric curve, right? We want to describe that using parametric equations, okay? And so how do we do that? Well, we got to first understand the dynamics that are going on here, okay? So we want to describe the center, okay? So the center is staying at the same height, right? So how would we describe the position of the center, okay, using parametric equations? Well, so this is x, so this is the x-coordinate, this is the y-coordinate, okay? Notice that this is how high above the x-axis. Well, we can see that it has a radius, right? It's one radius high, right, above the x-axis. Okay, so let's call this distance A, okay, which means this distance would also be A. Okay, so how would we describe the y direction, right? So again, we want x and y. So again, let's look at the center. So the center, we have x of t and y of t. So how do we describe the position of the center? Well, since it's on a flat curve, it's going to be the same, right? This is always going to be A above the x-axis. So y of t is going to equal A, the radius. Okay? Now what about x of t? What about the x-coordinate? Well, the x-coordinate is changing as this rolls, right? So it's moving along the x-axis, okay? But x depends on t as well, because as t increases, right? So time, right? Let's say this is moving at a constant speed, right? So at time, t equals time, let's say. So for every t, this is going to increase by what? By a multiple of the radius, okay? Because if t equals 0, well then what is x? 0. If t is equal to 1, right? If t is equal to 1, how far would I be? Okay? Well, in this case here, we can define it as, 1 unit, right? So if y of t is equal to a, we can describe the center x of t as a multiple of a. So we could write it this way. A times t. So these would be the coordinates of the center for any value of t. Okay, so this would tell us where the center is located at any time, t, if you will, if t was time. Okay, so y of t is always the same. It's going to be a, because it's constant, right? It's a circle. So it's always going to be the same distance above the x-axis as it rolls. The center is just going to be a distance from the y-axis, okay, over t, right, for some value of t. So it just keeps going further and further. So we can just say, hey, it's just going to be some multiple of the radius, right? So if we're here, right, so at 0, the radius, the distance is going to be 0, but if we're here, as it's rolling, the center is moving away from the y-axis, okay? And so the distance is always going to be some multiple of the radius. Okay, so we can define it that way. Okay? Now, what about the chalk mark? How can we describe the position of the chalk mark that's on the tire of the wheel, let's say, or on the edge of the circle? Okay, so it's rotating around the center on a circular path as the circle is also moving left to right in a clockwise direction, whereas moving left to right on the x-axis. So now a possible parameterization of this would be, let's look at this. So if I make a right triangle here, okay, then what I can do is there's an angle. So right, in this case, remember, t is an angle, right? So I can write this in terms of the component vectors. So there's the x component vector right here, and there's the y component vector here. So I can write the distance, right, the position of this with respect to the center, right? So with respect to the center, let me say, I'll just say point on edge of circle. Okay. So relative, with respect to the center here, what's that going to be? Well, that can be x of t is equal to, in this case, it's going to be what? It's going to be sine sine t, right? So x, so this distance here, x of t, and so in this case we're going to use sine of t. Sine t is opposite over hypotenuse, right? So that means I'm going to get, let me do it over here, sine t equals what? It's going to be x over a. Or in other words, x of t, right, is going to be a sine t, okay? So that's one. And then similarly, I can do cosine, right? Because then I got the y direction, so cosine t is going to be adjacent over hypotenuse, which is going to be y over a. So then I can get y of t equals a cosine t. Okay, so those are two possible parameterizations, right, for describing the point or the position of the chalk mark on the wheel as the wheel is rotating, right? So again, with relative to the center. So as this is rotating, right? So again, assume this is just stationary and it's just rotating. So these two equations would give you the position of the chalk mark as it's rotating around the center, okay? As if the as if the wheel wasn't moving, right? It's just spinning in place. Okay, so think of that. So there's this one. This tells us the position of the chalk mark with respect to the center as the point moves around clockwise. Oh, by the way, since we're moving clockwise, we're going to want to make these negative. Okay? So these are going to want to be negative. Okay? And the reason being that they're negative is because of the fact that we're going clockwise around the going clockwise as the wheel is moving left to right. So it's moving clockwise. Okay. Now, how do I put these two things together? Okay, so obviously the center is moving, right? The center is moving left to right. So we've got the position of the center as it's moving, right? But then we've also got the position of the edge, the point along the edge of the circle as it's rotating around the center. So that's this. So how do we put these together to describe the path that the point is taking as the wheel is moving? So we're going to add these together, right? We're going to add these together because it's going to be the position here and it's going to be plus whatever the position is here. Okay, whether it's negative or positive, right? So if it's here, we're taking this and we're subtracting. If it's up here, we're adding. So again, depends on the sign, right? That's where the sine and cosine come in. So we're going to add these two equations, and that's going to give us the parametric equations that represents this parametric curve right here, okay? So let's do that. So we're going to get x of t is going to equal at minus a sine t, and we get y of t equals a minus a cosine t. And then of course we get our final result by just factoring out the a. So we're factoring out the a and we get a equals t minus sine t. And we get y of t is equal to a times 1 minus cosine t. And those are the parametric equations that describes the path of what we call the cycloid. See you next time.